Welcome back, function folks, for part two. Here we go. This is the question that's been sort of plaguing us, just like C from the 3-minute review there, since grade 11. Wouldn't it be nice if we knew how to get this exactly? And now we do, right? We just take the log base 10 of both sides, log base 10 of both sides. That's the operation that gets the unknown out of the exponent and onto ground floor, and then it's a calculator problem. Okay, divide both sides by log 5, jam that into a calculator. By the way, this is exact, and maybe we would be fine with that, but often we like to get an approximate answer, which is around 2.64. This one, nasty question. If you ask, I'll put my solution to this one on, but there's one just like it in the textbook. So this is a connect with your textbook moment, and you can read one that's kind of like this, where the bases are different. It gets a little nasty, but you can try that one in the uh, in the textbook. Read that one. On to C. All right, this one is a little bit different. It hopefully kind of looks like something, right? It kind of looks like a trinomial, right? This is the first term, there's the second term, there's the third term. It looks like a trinomial. And in fact, in the place of that middle term, there's a 3x. So does it look like this? Where this is, where the a is kind of like the 3x, 3 to the exponent x. This is quadratic form. And we've seen this little trick earlier when we did polynomials, and again when we did trig. Basically, we're going to solve a simpler problem here. This is grade 10 problem. I can factor this, I think. No logs necessary at all. Numbers that multiply to get 27 and add to get 12 are 9 and 3, negative 9 and negative 3. And then now I've got the answers a equals 9 and a equals 3. So fine, dandy, those are the answers. No. Remember, we solved a simpler problem. A is 3 to the exponent x, and a is 3 to the exponent x. And so now I've turned this into two smaller exponential equations, these are grade 11 type equations, right? So this is 3 squared. I could take log of both sides if I want to, but I do see that my solutions are x equals 2 and x equals 1. Now, notice this solving a simpler problem business, again, if you don't like that, if you don't think that's you can see that it's quadratic form or not, you need to still show a step. So you would actually factor this one like this. Okay? So it's either that or that. This is the way I think of it. Solve a simpler problem. That was the strategy. Onward we go here. Onward we go. Hang on, what happened to C anyway? This is D. Where's C? Oh, there it is. Sorry, folks. A little bit backwards. You'll manage. What's the strategy here? Well, this is funny. It looks like all of these could be powers of 2, right? We solved this one in the 3-minute review, and it was easy because I could just write both sides as a power of, I think it was 8. Was it 8 or 7? 7. And then I can see x equals 7. This is similar because all of these are powers of 2, right? I can write this as 2 to the exponent 1. 4 I can write as 2 squared, right? 4 is 2 squared. Now the exponent is still on there, right? I got to be careful. This thing's here's 4. There's that bracket. 8 is 2 cubed, right? And so now I've got some exponent rules to do. This is 2 to the exponent 1. This is 2 times 2x minus 1, and this is 3 times x minus 4, but Now I've got some exponent stuff to do, and this isn't so bad. Probably this type of question, you might have saw a version of it in grade 11. Add the exponents when I multiply two powers there. Oops. Right? Add the two exponents when I'm multiplying. And when I have two bases with the same power, the exponents are the same. And notice we could think of applying log base 2 to both sides, but we know that when the bases are the same, the exponents are the same. And now it becomes a grade 9 question, right? Subtract 3x from both sides, add 1 to both sides, x equals minus 11. And dandy, easy peasy. That one's not bad at all. No logs necessary. All right, and then we did D. And now finally, oh, the light at the end of the tunnel, but this is actually a pretty tough question, this one. You probably haven't seen one like this, and so this will be a minute or two before we get through this guy. What do we have? This is not quadratic form because it's not like I have this sort of thing, right? Where one is a square of another, right? It's not that at all. And notice 246 isn't a power of 9. Right? So it seems like our strategies that we have so far aren't working. And it's not like I can take the log of both sides, because if I thought about taking the log of both sides, what would I have? And don't write this down because it's not right. It's not going to work. I don't have any formula, even though this is a number. I don't have a log rule for the sum of two powers. There's no log rule that will help me simplify this. So this I'm stuck with as well. So this is time for a new strategy. But let's have a look at what we have. Essentially what we got here is just a bunch of 9s. Whatever the value of x is that's going to solve this, this is like 9 times 9 times 9 times 9 times, a whole bunch of 9s, a whole bunch of 9s, 9, 9, a whole bunch of 9s. And what's this? This is a whole bunch of 9s. You know, a whole bunch of 9s. And don't write this down, by the way. This is going to look a little goofy. This is like my rough work here. Which pile of 9s is bigger? Well, this has got more 9s. In fact, it's got 2 more 9s, right? Because if this has got x plus 1 9s, this has got x minus 1 9s. This one has got 2 fewer than that one. So essentially what I can do, if this is just a pile of 9s, that means a whole bunch of 9s, and I don't know if 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, I've got a common factor of a whole bunch of 9s, right? I can call that x minus 1 9s that are a common factor. That's pretty weird, but certainly I can factor that out, and I'm going to. So there's actually a common factor of a whole pile of 9s. How many? Well, the smallest number, which is x minus 1 9s. Now what am I left over with? Well, I'm left over with 9 squared, and then when I take 9 to the exponent x minus 1 out of there, I'm left with just 1. The 246 stays put. And what have I got? Well, this bracket here is just 81 plus 1. And 81 plus 1 is 82. Then I'm guessing if I divide both sides by 82, this will go evenly. And in fact, it does. That's 3. And again, now I've turned this awful looking thing into a grade 11 type equation, right? I can write both sides with a power of 3 if I wanted to. I suppose I could take logs of both sides, but 9 is just 3 squared. And now I've got powers with the same base on both sides. I can make the exponents be equal. And now it's a grade 9 equation. I've turned a grade 12 equation into a grade 11 equation, now into a grade 9 equation, and there's my answer. What was the new weird step was this idea of recognizing that this is just a pile of factors that are almost all the same. So I'm going to take out the biggest pile that I can evenly. Well, which is the biggest pile that I can take out evenly is actually the smallest number. And in this case, this pile of 9s was smaller. It was x to the exponent, 9 to the exponent x minus 1. Lovely. There's a couple like that in the book, and they're tricky. You might want to look in the textbook for another one like that to read, or of course, you're always welcome to ask about that in class. That's it for the exponential equations. I wonder what a log equation would look like, or how to solve that. That must be tomorrow's stuff.